So hello everyone, thank you for being here. As I said, my name is Andrea Rausa and I'm working on the implementation, or not? Yes, okay. On the implementation of the gamma theta transition model within SU2 and its coupling with the Sparta Maras and K omega SST tolerance models. So this work is okay. No. C'è il wifi. So this work is within the project Mona Lisa, which is funded by the European Union. So why transition? Because it's cool, of course, but also because modeling transition equals to being able to include more physics within our simulations. So for example, transition itself from laminar to turbulent increases the encryption coefficient. Thus, fully turbulent simulations will result in higher dark coefficient predictions, and whereas transition simulations will decrease this D, hopefully more in line with experimental results. So we predict transition, we can do it with DNS or LES, but as we know, they are really costly and not industry standard for the moment. The transition models. We have three main transition models, which are non-local methods, for example, the N factor or linear stability analysis, which are really reliable, but they are not suited for modern safety codes, but they will prove me wrong. And since they require non-local informations, which are not really available in unstructured safety. Then we have the local methods without correlation functions, like the low-Reynolds methods, which again can be used for or are already implemented in unstructured safety codes, but they are not calibrated for transition, so they do not give results, good results really often. And in the end, there are local methods with correlation functions like the gamma theta that I'm going to present you, and also it's a skinnier version of the gamma model, which are suited for massively parallel codes since they rely only on local informations which are really available, and also they are calibrated with respect to transition experiments or higher fidelity simulations empirically. So the gamma theta model introduces two new equations, transport advection and diffusion standard with the boundary conditions for two new variables, the intermittency gamma and the theta theta. So intermittency is defined as the ratio of time over the total one in which the flow is turbulent. So if it's 0, then the flow is laminar. Between 0 and 1 is this transition region, and 1 fully turbulent, and can be also higher than 1 in case of full separation. Then we have theta theta, which is the momentum thickness reference number, which is defined as a non-local quantity. But through correlation functions, can be defined on local variables only, and this is used as a transitional separation. The model can be augmented in order to introduce also separation-induced transition. So, for example, we define a new intermittency, the effective intermittency, as the maximum between the intermittency and the separation-induced intermittency, such that we can also predict transition into separation. Once we define where the variables that we are working on, we can couple the transition model with the turbulence one, and I'm here reporting how to do for the K omega SST and the Sparta Maras models. It is quite simple, I would say, since it is just coefficients from pre-multiply the destruction and the production terms in the turbulence models. It is dependent on the value of intermittency, such that if the gamma is 0 laminar, the production is 0 too, so turbulence does not increase, whereas as gamma increases, also the production increases, and so for this turbulence. To detect the transition locations, a well accepted unit of measure is the turbulence index. which is kind of the same as like the intermittency, since it is from 0 to 1. Again, 0 being linear, 1 for the turbulent also can be greater than 1. Here I'm reporting how to compute it for k-omega SSD and Spark Mars, and it is more like a post-process after the computation. We can compute it on the surface of the body we are interested in. So here I'm reporting a comparison between the surface covered by the effective intermittency for our test case that I'm going to show you later on, and also the turbulence intensity, the turbulence index on the bottom, and we can see that really doing well. So we can define the transition location in this way. Regarding the implementation, there are mainly 3 changes on the C numeric, CC solver, and C variables classes. They are essentially the same for all 3 of them, where we create a new class, parent class for the transition, and then we modify the respective turbulence classes in order to couple transition and turbulence. So, for example, for the variable, we duplicate, so Pedro is going to hate me, the secure variable into the 3C trans variable, and we can talk about if it's needed or not. Here, I don't think so, but probably yes. Then we create a C-transforming variable, which contains all the correlation functions for the transition set and the computation models for the values that are needed for the transition. Then we modify the SSD and SA in order to couple transition mode. For the solver, again, the same. We copy the term solver, but in this case, we also modify it in order to be able to restart the simulation. And we create the trans-element solver, which, as always, contains the management of the residuals computation and also the communication between numerics and variables. And then we modify the SST and SA solver, especially in the post-processing, in order to compute the turbulence index. In the end, the numerics is again the same story. So we create transition folders with the computation of the convection, diffusion, and sources terms, and then we add the coefficients of the production and destruction term of the turbulence models within the term sources class. So as test cases, there are 4 of them right now. One is the flat plate test case, 2 are 2D airfoils, and the last one is a 3D test case, mainly for the cross-flow stability transition. So the first one is the flat plate, which is a series of experiments from the epoch TAC on the flat plate with increasing turbulence intensities on the free stream, such that we can range from natural to bypass transition. And here I'm reporting the values of the test cases. As a case setup, it is an incompressible case, so we run a second order scheme for the compressible run solvers, and first order for the turbulence, and the convergence of the results. So the results of considered conversion is the RMS of the residual of the pressure is lower than 10 to the minus 12, and the grid is fully structured. So here I'm reporting the results for the flat plate in terms of the scheme friction coefficient with respect to the Reynolds numbers X on the plate for the 4 test cases. And we can see that the green line is mainly in agreement with experiments, which is the green line is the SSTLM being LM, the transition model. I call you like this from your own. However, when we couple the LM model with the Spark Mars model, it seems that something doesn't work, especially for the T3A and the T3A test cases, since there is some training phenomena. But this is not encouraging right now, but I assure you that the results will get really better from now on. So there is something wrong, probably with the configuration file. Regarding the 2D airfoils, we have the Epler E387 and also the natural laminar flow 0416 airfoils. Even though the Mach number is really low, they are considered compressible test cases, and we have the CL alpha, numerous experimental results compared. So we can start for the Epler, which is an O-grid, standard O-grid topology. Since it is compressible, we run raw, second order. Again, for the turbulence, we only have the first order, and here the convergence is for residual on the density. So it is less than 10 to the minus 30. Here we can see the CP, minus CP, over the normalized x-coordinate of the surface of the airfoil. And we can see that the transition models really improve the solution in respect to the fully turbulent models here, because there is the formation of a laminar separation bubble on the upper side of the airfoil, which can be seen also here in the flow field colored by the x component of the u velocity. So here is for 0 degrees angle of attack, is for 6 degrees angle of attack, and we can see that transition really works. But we can also see that with respect to the BC current transition model, which has already been implemented in SU2, and it's an algebraic model only for spiral matters, we can see that at 6 degrees angle of attack, the prediction is much better for the LM model. So we can say that being it based on partial differential equations, seems that it works. At least now. We can also see the CL alpha and the polar for the profile. And we can see that the real advantage of the transition model are in the polar, so in the prediction of the drag coefficient, where the turbulence model really fails. I mean, they get the trend, but not the value. But instead, in the transition model, we can also get values. So, and there are some staggering results for the BCs, it's sometimes it doesn't converge. For the natural laminar flow test case, it is a structured field hybrid with a C-type topology for the far field, and the test case is the flow versatile is essentially the same as the epic one. Here I also put convergence results, since this is a test case from the first AIW transition workshop. So they provided 5 different meshes, which I used here. We can see that the convergence is quite tricky. So SSTLM and SLM seems to converge at 4 and 15 degrees angle of attack, but not in the cross cases. And at first glance, it seems that there is a problem of convergence. But if we go deeper, if we plot the results for the polar, the CL alpha curve, we can see that for the fine mesh, which is the medium one, I would say, so the third one, we have really good agreement for the CD, better if we draw scheme for the transition models with respect to the fully turbulent, and this is okay. So this is what we expect. But if we refine again the mesh, so we use the ultra fine refined mesh, we are getting worse solutions. So the transition, the CD is a little bit worse with respect to the fine mesh, and also there are some problems of convergence. It is kind of seems to have over refinement problems, where we already know that the plane of the runs does not converge to a solution. I mean, to the real solution, if we refine again, probably this is the case. I mean, it needs some further investigation. So the last test case is the 3D one, where we have cross-point stabilities, since it is a 3D test case with a shape that allows for this kind of phenomena. It is operated spheroid or ellipsoid, and for this test case, in the model, it has been augmented with the corrections for the cross-point stabilities, and here on it will be called LM 2015. So here also there will be mesh convergence, and the results with respect to experimental transition lines for 10 and 15 degrees of angle of attack. So here again the mesh is hybrid, and it's the same sort of stuff is an incompressible in this case as the flat. The convergence results are reported for 5, 10, and 15 degrees angle of attack with 3 different meshes. First trend that we can see is that the coarsest mesh gives higher CD. This means that it tends to predict transition earlier, since the surface that is turbulent on the ellipsoid is much higher, and thus CD is higher. But then the CD decreases, and we can see that we have almost convergence, probably with some more refinement, but we have some strange behavior of the SSTLM 2015, which I do not really know how to explain, but probably there's something wrong. both or probably not. So here probably there is a convergence problem in the simulation. So here are the results for experimental results. So in yellow dots are the transition lines experimentally found, whereas the surfaces are covered by the turbulence index. And on the left, we can see the non-augmented version, whereas on the right, we can see the augmented version with the cross-point stabilities corrections. And we can see that at 10 degrees angle of attack, the prediction is really better with the augmented version with respect to the non-augmented one. This trend remains with the 15 degrees angle of attack, where the cross-point stabilities are much higher again, and we can see again that the augmented version is just like orders of magnitude better with respect to the especially for this test case. So in the end, the work done is the implementation of the gamma to the model, and it's copied on the Sparta, Mars, and K-omega SST turbulence models. The implementation of the turbulence index as post-processing for the turbulence models in case the transition model is active, and a preliminary validation of 2D and 3D test case. Now we're working on simulations of more complex geometries, like for example the common research model natural laminar flow, which is a full-scale 3D fuselage plus wing model, which is quite interesting. And then we are also testing the results with respect to other convective mental schemes, just to see if the results will change much or not at all. In the future, there will be also validation on wind turbine blades, so that we can check also the periodicity boundary conditions, and validation on state test cases. We check for some of those. The implementation of the automatic differentiation codes within the model, because for now there is none. And probably in the future, the implementation of other transition models. So, for example, the skinner variation of this model here, the demo. So, thank you for your attention.
Room for questions in the audience. Yeah.
Hello, it was really nice, especially the airport, seeing the I was wondering how the competition costs compare to
With respect to the turbulence simulations, or
yeah, just the simulation that was ran.
okay. So the question was about the computational overhead of the transition models with respect to turbulence simulations. So for now, the code is not really efficiency really focused, because there are a lot of savings or a lot of variables in order to check for post processing, which is if there are any problems or not. But in terms of efficiency, I would say that there is not that much impact on the cost per iteration, because there are only 2 more equations to be solved. But there are some changes in the convergence history. So although they are not like they are not like in the same thread always. So probably sometimes the transition model, the simulation with transition model converges faster with respect to fully turbulent. Sometimes it converges slower. It depends just on the case. But the cost is not that much bigger with respect to what we obtain.
Thank you. Any further questions?
No, maybe one last from me. So do you have any plan also to run some compressible flow test case?
Some compressible
flow?
Yes.
So whether
the really compressible flow, so the Epler and the NLF were run as compressible, even though they have low Mach number. Really compressible are the CRM and LF. So this one here, which you can see here. So this is a preliminary run for this. Where there is a plan for sure, because we have to validate also for compression simulations. Right now, at the moment, I'm having troubles with the turbulence only solution here. So I'm having troubles of converging to a solution with a turbulence only model. And then the transition, I don't know what will happen. But yes, of course, it will work.
It would be interesting to know.
Yes, sure.
Comes up.
So I guess no further questions. Thank you very much again.